Okay, for today's class, we're going to cover Chapter 28, Sections 1 through 2. We're going to apply those concepts, which you have diligently studied already, to concept questions 1, 2, 3, 9, and 10, and then exercises 1, 2, 3, and 5. Take a look at those problems, and come back here, and we'll start with concept question 1. Okay, so we have these 4 resistors in concept question 1, and you're given voltages across each one, and you're given the resistance of each one. You're trying to rank the currents flowing through each one. So what's the main idea? The main idea is Ohm's law. So we can write Ohm's law as current equals the voltage over the resistance. So that's how we find the voltage across a resistor, is we note its resistance and then we note what current flows through it. Or if we know the voltage across it, let's say hooked up to a battery, then we can find the current flowing through it. Okay, so if we just decide to choose delta V to be 2 volts and R to be 2, then we can just reference everything in terms of this. So this would be IA, and therefore IB would be how much in terms of delta V and R. Okay, so it's half the voltage, and the resistance is the same. So that gives us 1/2 IA. All right. Well, what about IC? How much is it in terms of the voltage and resistance of A? Well, C is the same voltage, but it is half the resistance. So that's going to give us twice the current in A. And then ID, well, we've got half the voltage, and we have half the resistance, so that is equal to IA. So again, we applied Ohm's law for these resistors. Okay, moving on to number 2. Look at that one while I draw it. Okay, we have this light bulb, and the bottom of the light bulb is touching the positive button of this battery. Does the light bulb light? Okay, the answer is no. Okay. The reason is because in order for the light bulb to light, current has to flow. And flow means there has to be a sink and a source, but in electricity, you can't have current building up. Charge can't build up somewhere. So current can flow through the battery, through the light bulb, but it's got to come back to the battery, which means there has to be a way of connecting this to the bottom. And if you look carefully at a light bulb, an old incandescent light bulb, they have 2 pieces of metal, the kind of the coil part that you usually screw into the socket. It's got a little metal button at the bottom, and it's separated by usually a little black membrane, or it's a plastic piece that separates these 2. And if you were able to cut that open, you'd see that one side of these wires goes down to the bottom button, and the other side of the wire connects to the side casing. And that allows us a path. We have a path for current to flow through the light bulb, out and back through the battery. And that allows current to flow, and therefore allows the light bulb to light up. So you can't light up the light bulb without that full, complete path. So I like to say it's a circle. It's got to be a circle or a loop. You have to go all the way around. Okay, let's take a look at number 3. Okay, so we've got the symbol for our battery, resistor, and then a broken wire, points 1 and 2. The question is, what is the voltage across points 1 and 2? What is delta V12? Well, how are we going to find that out? Let me ask this question. What if we got rid of this resistor and it was just a wire that went from here to here? What would it be? It would just be 3 volts, right? Only this would be, it would be a negative 3 volts drop from 1 to 2. Okay, but it'd be just 3 volts because they're just wire connecting, conductor connecting, so they'd be at the constant potential. And so these two spots would be at the same voltage as this battery. With the resistor in there, it has the potential, well, I was playing words, it has the capability of dropping the potential because it can dissipate some energy. But that's only by Ohm's law. So here would be the potential across the resistor in magnitude would be equal to IR. There is a resistor, but is there any current flowing? Because of this break, no current can flow. Current cannot flow through that resistor. There's no place for it to go. If I jumped those, then suddenly current can flow, and I would get a voltage drop across the resistor. But with that break right there, with that being broken, then no current can flow, and therefore this equals 0. There is no potential drop across the resistor, and it's like it's not even there. So delta V12 is equal to 3, with 1 being at the higher potential and 2 being at the lower potential. So remember, voltage drops across resistors require current to flow through them. If current's not flowing through them, by whatever means, that means that there's no potential drop. Okay, let's jump to 9. So we've got here's 2 light bulbs, A and B. Okay, and then we have this battery or power or voltage source. Okay, and so the question is, the switch gets closed, and does the light bulbs get brighter, dimmer, or go out? So how are you going to figure that one out? First of all, brightness is a measure of power, which we'll get to in the next reading. But when these resistors or when these light bulbs are the same, that means they have the same resistance, and so brightness is just a function of current. And so the question is, what's the current flowing through these? When I flip that switch, does the current increase, decrease, or stay the same through bulbs A and B? Okay, so let's think about before the switch is closed. With that open, no current can flow through here. So the current's flowing through A and through B and back. And therefore, the current through A and current through B are the same. So since they're the same resistance, that means that these have the same brightness. When I flip this switch and it's closed now, okay, current comes through the battery, through A, and it hits a junction, and some current can flow this way, and some current can flow down. Now, if you're an electron, and you see a path to get to the back end of the battery, and you have to go through a light bulb, which is a resistor, or you can go through this bare conducting wire, which path would you take? The idea is that electrons will take the path of least resistance, okay? Now, since this path has technically 0 resistance, all the electrons will go this way. Technically, it'll have a little bit of resistance, so a very small amount will go through here, but so small that it's not going to light up the light bulb. Okay? And so, in this case, B would go completely out. So B goes out. In case A, though, what's happening? Before it switched, the battery was trying to push current through A and B, and therefore the load that it feels is the sum of these two. It's got to push it through 2 things, which means it's got a greater resistance. And so that means the current is smaller by this rule. Same battery, but larger resistance, and so the current is small. When I close this switch, suddenly this is out of the picture, and the current is only flowing through 1 resistor. The resistor is now smaller, same battery, so the current increased. So more current is able to flow through A when it's alone in the circuit than it is to flow through A and B together. So A got brighter. Okay, we have another one, 10, that's similar. Here's my light bulbs. This is A, this is B, and this is C. All right. Now, right now in this picture, the question is rank the brightnesses of the bulbs. So think about what we learned from this picture and apply it to this one. Okay. So hopefully you're able to see that A is going to be brighter than B, which is equal to C. Why? Well, first of all, they're identical light bulbs, which means their resistances are all the same. So brightness is just a function of current. And whatever current flows through A, it's got to split up and go through B and C. So there's more current flowing through A than it is going through B and C. So it's greater than B or C. Now, why are B and C equal? Well, if they're identical bulbs, then when I'm an electron, I get here, there's an equal probability of going here or here. Or if there's 100 electrons that get to this point, well, 50 of them are going to go through and 50 are going to go through here because there's no preference to the path. Okay? The resistance at each path is the same, and so it's going to split and go through either path equally. That's why B is equal to C. Now, part B of this problem says, what if I take a wire, just a simple conducting wire, and I bridge this gap? So I connect it between points 1 and 2 here. The light bulb's still there. It's still in the circuit, but now I have this wire connecting it. All right? Now I'm going to draw it a little differently. That's the same thing as if I have another piece of wire that connects across that light bulb C. What happens to the brightness of A, B, and C? Okay, think back what happened to this one. B went out because now the current that got to this junction had an unresistive path back to the battery. Same thing happens here. All the current that gets to this junction has now a path to get back to the battery. So C goes out. And so does B, because there is still that B and C are in parallel with a bare wire, and so that current can flow and just totally bypass B and C. So they go out. What happens to A? It gets brighter for the same reasoning that this got brighter. Now, instead of having a resistor with additional resistance later on, and the battery having to push through both, it's just one resistor, and so it can push more current through it, and so the A gets brighter. All right, very good. Now let's look at the exercises. Okay, so let's take a look at exercise 1. Okay, the big idea here is to try and translate pictures, physical things, into a diagram. And so here's an effort at drawing a physical picture. We've got this battery here. Try to draw a physical battery here. And it goes through, these two resistors back here, and then another wire that goes like that. That's the picture, and we need to translate that into a diagram. So I'm just going to call this R1, R2, and R3, and this would be delta V battery. So how would the diagram look like? Okay, with this diagram, we've got a battery, which I'm going to go ahead and put over here. All right, and wire comes off the top of it. Let's just focus on this one right here. Okay. We've got a wire going through one resistor, which I'll put right there, and then another piece of wire and goes through another resistor directly. And then that wire gets back. It gets back to where it started. Okay. And then what about this one? Well, this is connected to the top of battery 2, so I could bring another wire out of here, or I could connect right here if I wanted to. Or I could connect it anywhere, as long as it's connected with a wire to the top of the battery. So I'm going to go ahead and make a junction here instead. And here's my resistor. And this connects to the bottom side. Well, I'll just connect it right there. Okay. So this is R1, this is R2, and this is R3. Now that's not the only way of drawing a diagram that represents this accurately. I could have had the resistor on the other side, but what's important is that the paths are consistent. So the path from the top of the battery can get to the top of R1 or R1 and R2, and then R1 and R3 are connected, or R2 and R3, I apologize, R2 and R3 are connected with a wire without any junctions in it. And then the bottom of the battery is connected to the bottom of R3 and the bottom of R1 via a conducting path. And that's all that matters. I don't have to have specific wires going in the same directions. I can try and draw it as simply as possible to make sense of it. Okay, let's apply that to 2. This one's a little more complex, so I'm going to draw it here, but you go look at it and see what you can make of it. Battery and I'll call this R1, here's delta V battery, here's R2, and here's a capacitor. How could I draw that as a diagram? Okay, I'm going to draw one that looks like this. Okay. Now that's not complete yet, but what I've captured here is what part of this physical setup. Got the battery and one wire coming off the top of it to the top end of R2. So I'm going to call this R2. And there's no junctions. There's no junctions. And then R2 goes through the capacitor, which gets back to the battery. So this is our capacitor, gets back to the battery. So how do I attach R1 to that? Where can I connect it? Well, I know R1 has to be connected to the bottom side of the battery, so that can be connected anywhere here. This is all connected to the bottom side of the battery. The other side has to be connected in between R2 and the capacitor. Well, in between R2 and the capacitor is right here. So I can go like this. And that is the correct way of describing it. Again, I could have put it somewhere else. I could have put it from over here to over here. That would still, from here around over here, but that seems more complicated than is needed. So this works out well. This seems to be a simple way of diagramming that. All right, let's do 3. Okay, so on 3 we've got a resistor coming into a junction, another resistor, and we're told the resistances, R1, R2. We're told the delta V's. Hold on. Yes, we're told the delta V's. We're told which side's positive, negative, plus, minus, and this one is plus, minus. And we're asked, what is the current here? Okay, now to help out, I'm going to define a current. So I'm going to call this 3, and there's current I1 here. But my question is, what direction is current flowing? If this is plus and this is minus, then what direction does the current flow? It flows from the positive to the minus. Okay. So I know current I1, I'll call it I1, is flowing that way. And likewise, current I2 is flowing that way from, my bad. From plus to minus, I apologize. So it's flowing outward, plus to minus. So our question is, what is I3? So what rule are we going to use to be able to solve this? Find I3. It is the junction rule, or the node rule. And so I'm going to make a guess that I3 is flowing out. Okay, I'm going to make a guess I3 is flowing out. And maybe I'm wrong, but we'll just see. So I've got I1 is flowing in, I2 is flowing out, and I'm making a guess that I3 is flowing out. Okay, so I3 then is equal to I1 minus I2. Right? Now I'm not given the currents. How do I find the currents from what I am given? Okay, using Ohm's law. So I can write I1 is delta V1 over R1 minus delta V2 over R2 for I2. And I've got the numbers there. Delta V1 over R1, that is going to be 2 amps. We get 2 amps here. And delta V2 over R2, that's 15 divided by 5 is 3 amps. And I get a negative 1 amp. So there is 1 amp of current flowing along this wire. And what direction is it flowing? Into or out of that node? It's flowing into the node. Why? Because I assumed in my calculation it was flowing out. This is in, this is out. But I got a minus sign, which means I was wrong. So it's flowing into. So the current here is flowing that way. Into. All right, so that was an application of Kirchhoff's node rule or Kirchhoff's junction rule. Let's go ahead and do the last problem now. Number 5. So take a look at number 5. All right, so we've got the system, a battery, 1 resistor, another battery that's upside down, and a wire connecting the two. I'm going to call this delta V1. This is R, and this is going to be delta V2. And the first question is how much current is flowing through the resistor? Which is the same thing as saying how much current is flowing through the loop. Because it's one loop, there's no other paths for the current to take. So whatever goes through the resistor must go through each of the batteries. Okay, so I'm going to make a guess, or just I'm going to choose a direction. I'm going to choose the current to be flowing that way. So across this resistor, current flows that way. And I'm going to go in the direction of my proposed current. So I'm going to start in this corner and go all the way around. Okay? And so doing that, I'm going to do this loop rule. I'm going to gain potential here because I'm going from the small bar to the big bar. So I get a plus delta V1. I'm going in the direction of current across the resistor. So it's a loss. So I get negative IR. I go, continuing on, I go from negative or small bar to big bar, which is negative positive. So I gain delta V2, and I get back to where I started. So that is equal to 0. And so solving for the current, I get I equals, take this other side, we get delta V1 plus delta V2 divided by R. If you plug in your numbers, you're going to get half an amp. So there's half an amp flowing through that resistor. Now, the second part of the question says, plot the potential as a function of position along this loop. And so to help, I'm going to define some positions. I'm going to draw some dots here. Okay. In this lower corner, I'm going to call it A, then B, then C, then D, E, F, and G. Okay. And I want to plot the potential as a function of those locations. So this is A, B, C, D, E, F, G, and A again. Okay. We're going to plot the potential, V. We'll just assume that the potential at A is 0. So we start right here. So as you go from A to B, do you gain potential? Do you lose potential? How much? Does it not change? And then think of that logic all the way through. So from A to B, do we gain potential, lose potential, or does it stay the same? It stays the same because it's a bare conductor. So the potential is the same everywhere along this bare conductor. So it's 0. If it started at 0, it stays at 0. Now going from B to C, do I gain potential, lose potential, or stay the same? I go from the negative side to the positive side of the battery, so I gain potential, and that battery is a 3-volt battery, so I'm going to put a mark here at 3. Okay, so it's going to get up to here. So I gain 3 volts. And now from C to D, do I add potential, lose potential, or it stays the same? It's a bare conductor, just a wire, so it stays the same. And then from D to E, do I add potential, lose potential, or it stays the same? I'm going in the direction of current, so I lose potential. Now to find out how much, I need to do another calculation. Okay, I can make a guess, but let's go and do the calculation as well. So now that I know the current, I can find the potential across the resistor. Delta V across the resistor would just be IR. And so I get 1/2 times the resistance, which is 18, which gives me 9 volts. So I lose 9 volts. So that means I'm going to do the -3, -6. So at E, I've lost 9 volts. So I've got to go drop all the way down there. Okay, from E to F, same reasoning. I don't get any difference. And I go from negative to positive from F to G, and that's a gain of 6 volts. So I get up to there. And then from G all the way to A, it's no change. You know, like that. So that would be my potential as a function of position along the loop, assuming at A it is 0. That ends our discussion.